I really want to thank the organizers for inviting me here, and for the rest of you for listening to my talk, at least at the beginning. And my talk will move you even further away from mathematics. And I just want to say some few general remarks here. Last time I was in Cambridge, I was a condensed matter theorist, and right now I don't know what I am. But I've been very interested in cancer for the last 15 years, and we started a field which we call now physics of cancer. And as my profession at the National Science Foundation, I look at a lot of proposals every day, and I realized that whether you come from high energy physics or from mathematics or from condensed matter physics or from engineering, you have a very different view of what you should do about cancer and how you should look at cancer. And that's why diversity is very important, because we are trained in very different ways. And as a condensed matter physicist, I'm actually trained to look at data and try to cook up some simple mathematical models that can actually tell me what's going on, which is a different approach for people coming from high energy physics who actually try to do very reductionist kind of a modeling at the very details. The problem in biology, however, is that there is very little data. Even though we have great now methods to image things at high resolution, and we still don't know a lot of the parameters that enter reductionist models. And because of that, you could fit everything. As I don't know if you know that story, but there is a physicist who said that with 3 parameters, he can fit everything, the whole universe, and with 4, he can make it move. So I actually stay away from detailed models, and I'm trying to understand the data. And cancer is actually very nice field, although it's a nasty disease. But it's a nice field because it captures all of biology. It captures biology all the way from evolution, all the way to actually psychology, because the disease is so nasty that it affects actually people's psychology. So there is place for everyone who wants to try to understand that disease. So I'm going to talk here just with my shallow brain networks about what I've learned about tumors from oncologists. And I'm certified I can fake an oncologist for about 30 minutes, so I have to fill 15 minutes here with useless philosophy. So let me start actually first to explain to some of you, maybe most of you probably know, but for those of you that don't know, just to remind you that structure and function in biology are very tightly linked. And we heard yesterday very nice talks about growth and stretching and things like that. And one thing that one has to be careful though is that often there are feedbacks in biological function that are mediated by actually transcription that actually oppose a lot of physical changes to the system, because the system tries to be in homeostasis, as biology says. We call it equilibrium in physics. And so there are feedback loops that actually try to keep the system in equilibrium. And this is why we can live for so many years without actually really suffering as much damage, for example, as your car. You change it every 10 years, but you're able to live for 70, 80, 90 years, and hopefully more. And I just want to show you 2 examples here of function and shape that actually, on the left is a lizard that swims in sand. It's a very interesting animal because it uses the sand as a liquid and swims there, and with its motion it actually uses it in a liquid state. And on the right you see diffusion imaging of brain networks of a monkey, and this, we hope that all these connections actually, and the structure of these connections is very important for the function of the brain. And I want to say one thing that, in fact, I really am very thankful to Darryl Home, because when I was in Los Alamos, there were these big groups of applied mathematicians and then physicists analyzing the same data in a very different way. And I was trying to explain that we should combine the machine learning with actually physical models, because it could be helpful to machine learning to have some restriction. He was actually very supportive. I remember one meeting when he say, actually, that's right. We need to get the physical models and the mathematical data analysis together. And I think that this is very important. And for example, at the LHC in Switzerland, I've talked to the high energy physicists as well as the people at LIGO analyzing gravitational waves, and they stay away from deep learning algorithms. And the reason for that is that they feel that deep learning algorithms have hallucinations. And if humans have hallucinations, I don't see why architecture based on human brain wouldn't have hallucinations. So they use actually Bayesian analysis, and they use physical models as priors in Bayesian framework, because they feel that this is more clean statistically to actually analyze them. So, you know, whatever works, whatever you like, but in biology, one has to be careful because, again, when you analyze data without knowing what you're analyzing, you could see things that don't exist. So let me go back to biology. So one thing to realize is that actually the form of biological organisms is shaped by genetics and forces. And these forces actually have effect on the genetics, and the genetic transcription or the production of proteins is tightly linked to actually the forces. So it's a very complicated process that we don't fully understand, and I think that the differential geometry approaches have huge place to play. And another philosophical remark is that I think we are living in the same era like 100 years ago, when mathematicians developed all the evolutionary models in the 20s, and now in the last 10-15 years, biologists, physicists, engineers, and mathematicians are entering again that field, trying to understand the molecular basis of evolution. So I think the same way you have developed these wonderful methods for analyzing shape and form, now we want to understand how the forces and how the biology brings these shapes and forms. And then everything is going to be together, the analysis with the forces, with the genetics. And I think it's going to be wonderful, like we're seeing this huge renaissance in evolution, where molecular biologists and biophysicists and chemists and engineers are working together to understand how evolution happens in model organisms and, well, humans and so forth. So animals are formed, as you know, from a single cell that merges with another cell. And then from this thing, miraculously, all the possible animals on this planet actually come into existence. And this is possible because there is a program inside that single cell from which the animal starts. And that program miraculously also uses the biophysical and chemical laws that exist on this planet to form organisms that can live for a long, long time. And these embryonic stem cells, as they're known, the embryonic stem cells are basically immortal. We have had the same gametes for 6 million years, and they have not died. And so, to a large extent, we don't understand how is it possible for a cell to survive 6 million years, but it is possible. And because this is the same cell, so if you want to ask me, you can ask me after the talk why it's immortal, but it's immortal, it's the same cell, 6 million years. And after that, after the first divisions happen, cells start to differentiate. What that means is that they start to change from each other. The cell in a liver is very different from a neuron in the brain, but they came from the same embryonic stem cell. And through programs inside the DNA and expression of different proteins, these cells become very different cells. So one could look at this process as a programming steps, and try to, and that's what synthetic biologists are doing right now, trying to bring the computer scientists into the programming of cells and try to understand this as a program. Once the organism is formed, now these cells produce adult stem cells, and the adult stem cells are not as undifferentiated as the embryonic stem cells. For example, the adult stem cells in the brain are different from the adult stem cells in the colon, or in the hair follicle, or in the skin. However, they also can produce the whole organ in which they actually reside. So they produce cells which actually become more differentiated as they go in time. And then you produce these finely differentiated cells which do the function of the organ. For example, in the liver, it's a liver cell. In the brain, it's a neuron or astrocyte, and so forth and so forth. And they do the function that they have been made to do. We have actually advanced dramatically in the last 10 years in being able to create organs in a petri dish. So we can take these cells, and somehow these cells in a dish produce the organ from which they were extracted. We had problems until about 10, 15 years ago to propagate these cells for a long time. We didn't know what the media should be, we didn't know the conditions, but now we do. And so we can now produce these organoids, as they're known, and they actually produce the organ from which they come. And so now we can study a lot of things. We can also study, so these are 4 cells, so there have been 2 divisions, and we can now image actually the proteins inside the cell. So these are 4 cells, and the fluorescent red and green that you see are actually different proteins that have been labeled with fluorescent dye. So now we can see the distribution of molecules inside. We can follow them in time. We can actually start to understand the cell, how it functions. A lot of physicists have moved from neuroscience to cell biology, and in fact in neuroscience there are very few left. And that's because I think people realize that we could understand how a cell works, but we are far away from understanding how the brain works. In the brain, we don't even know what the questions are. At least here we know the questions. And so just to show you a few organs, for example, this is the colon. Colon is made of this villi. There was a paper recently by one of the infinite number of papers by Mahadevan in Nature. And he made a model of how the colon form, how these villi form, a mechanical model. Maybe it's true, maybe not. Then this is the mammary gland, the breast. Again, there are stem cells that produce the whole organ. And in tissue homeostasis, as I said, it starts with adult stem cells, and they produce differentiated cells. And in every organ, there are many, many cells. And these cells, I can give you some of them. These are, for example, the epithelial cells who do the function. There are fibroblasts that support this function. There are immune cells. There are hundreds of different cells in every organ. It's a very complicated system, and maybe it's even complex. Now, this tissue homeostasis was modeled a few years ago by a group at Oxford with Walter Bodmer, who is a famous geneticist in the UK, at Cancer Research. And they just put a simple model that is just first-order kinetics with nonlinear Hill kind of functions. And you have 3 populations of cells. This was for the colon. You have the stem cells. You have the more differentiated. They're called also transit amplifying cells sometimes. And then the fully differentiated cells are the 3rd set of equations. These are very simple equations. You can put them on the computer, and you get 3 equilibrium states for the number of these cells. And this was very nice. I generalized this model to include aging, because cells, as they divide, they lose part of the DNA at the ends, also known as the end replication problem, discovered by Jim Watson and Ulovnikov in Russia, in Soviet Union. And so you need to put aging, that is that there is finite number of divisions that a cell can do. And we've learned a lot about this also from hair follicles. Hair follicles have a different dynamics. Again, talking about shape and form and self-organization, the hair follicles actually periodically shrink and expand, shrink and expand. This happens in few weeks. So over the lifespan of a mouse or a human, this happens many, many, many times. Why they do that, we don't understand why, but there is something about renewing these cells because they exhaust their potential. Maybe they become cancerous, and so they have to be removed and then regrown from, again, a small number of stem cells. It's very interesting because the growth cycle is correlated among different hair cells, hair follicles. So it's very interesting that there was a proposition a few years ago that in order to cure baldness, in fact, it would be good to remove some of the hairs that you have around the place where the hair is not growing. because they're correlated, this will drive the cells, the hair follicles around this healthy hair follicle to actually regrow. And maybe this actually will happen. We'll see. But so it's a very interesting system where you have a many-body problem in the growth cycle. In the shrinkage cycle, they seem to be uncorrelated. Very interesting. We can model this again using reaction diffusion equation. It seems that there is a morphogene that is being released by some of the supporting cells that kills these cells periodically. And the reaction diffusion equation you can think of in the steady state has an exponential profile in space, and you can think that as you get closer and closer to the stem cells, there is less and less of this morphogene trying to kill the cells, and the stem cells survive. Maybe that's true, maybe it's not, but at least fits the data nicely. You can show that. And so we speculated that, in fact, the shape of or the topological structure of these stem cell niches, as they're called, might actually influence the way these cells divide. And I was struck by the fact when I was modeling this homeostasis and putting aging into the system, trying to understand how cells divide. And so what I really realized, that these equations are actually wrong. So the ones that actually the Oxford people with Walter modeled were actually is wrong. Why is it wrong? Because they assume that all cells divide randomly. But when cells don't divide randomly, the aging of the niche depends on the order of division. And you can show very easily that whether one cell divides until it exhausts, on the right-hand side, exhausts its potential, and then the next stem cell divides, exhausts its potential, then the next stem cell divides, ages very differently if the cells, like on the left-hand side, randomly decide to divide. So again, let me tell you the model. The model is that the number of cells have to stay the same. And that stem cell is going to divide, and then divide until, and the number is fixed, some cells are removed from the top of the column that are differentiated, and the stem cell divides to repopulate the column. Whether these cells wait for each other to divide, or they randomly decide which one is going to divide, changes dramatically the potential of these cells to divide, the number of divisions available. So these models that are continuous kinetic models are actually wrong, because you need to take into account the discrete structure of cell divisions. So makes things even more complicated, because now we don't have all the tools of analysis to actually analyze these differential equations. We have to go to difference equations. And so difference equations are much more complicated in order to solve. So you have to put them on the computer, and then the computer knows what's going on, you don't know, and becomes very complicated, at least for a simple mind like a physicist. So let me go and move now to cancer. And what happens to cancer right now? The main hypothesis will be given by a scientist at Johns Hopkins. His name is Bert Vogelstein, and together with Franziska Mikor and Martin Novak, they have cooked this model in which they say that there are a finite number of mutations that have to happen, and then cancer is initiated. Beautiful paper based on game theory, and it matches a lot of the data to be understood. For example, the age incidence of cancer doesn't go exponentially with age, but goes as a power law. And it goes as a power law. If you write the differential equations, you realize that the power of the incidence of cancer is actually the power of or the number of mutations that have to happen. If there was only one mutation that is necessary for cancer, then you would get exponential. But if you have two hits, for example, the so-called multiple hit hypothesis, that you need 2 or 3 or 5 mutations, then you would get power law to the power 4 for 5 mutations, for example. So this fits the data that there are a number of mutations that have to happen before cancer is initiated. And we actually see that. That's why we do breast cancer screening. That's why we do colon screening, prostate screening, because if you catch the cancer in the early stages when 1 or 2 genes are mutated, then you can actually remove it physically through surgery, and actually you're not going to get cancer. And in this particular paper, it was estimated it takes about 40 years to get colon cancer. And that seems like right. People that are born with one mutation usually get in their early 40s cancer, colon cancer. For the rest of the population, starts around 60, really to become significant. And this is a small sketch of this idea of this theory, that as time goes, they accumulate mutations, and they generate these stem cells, they generate these progenitor cells. And as the stem cell accumulates damage, then after some time, the red and the progenitor cells are at risk of becoming cancerous and starting to grow indefinitely or for a long time. And people have produced this so-called cancer stem cell hypothesis, which now says that the way organs actually form and they live under homeostasis through small number of stem cells, that cancers also have cancer stem cells that occasionally divide asymmetrically into a stem cell and a cancer cell, and that we can't cure cancer because we can't kill those stem cells. And the reason for that is that our drugs usually work on dividing cells, and so if these cells are not dividing often, then we can kill them because our drugs have no effect on them. And one of the main points here that I will make in a few minutes, we will address this hypothesis. So just to give you a little bit of an idea what happens in cancer, and that's why I called my talk loss of form, and you'll see at the end what I mean. But in general, there is a cartoon which says that in the normal tissue, the cells have polarity. They're organized in a polar way on the basement membrane. When cancer starts, it starts to divide randomly, and actually when it breaks this basement membrane, you start to have a stage 3 cancer. When it goes to other organs, you get stage 4. But the basement membrane breakage is a major event. And so I wanted to look at data of individual tumor growth before I start modeling it, because I have been several times wrong doing models that actually biologists say have nothing to do with reality. And so I start working with oncologists, and if you think that it's hard for a mathematician or a theorist to work with biologists, you have to try to work with oncologists. But on the other hand, it's very fruitful, and I created some opportunities in the United States, which I hope that will continue next year in Europe, for theoretical physicists, mathematicians, engineers to work actually with oncologists. Because I reasoned that the only place where a mathematician or a theoretical physicist will meet an oncologist will be in the oncologist's office. And that will not be a good place to start research at that time. So I actually put them together, and so there are some funding opportunities if you're interested. I'm very interested to work with the Europeans next year to bring this whole idea here. And I talked to a foundation called Stand Up to Cancer, which is in California. They're very excited about working with England and Germany and France. So let's talk after that. So when you go to oncologists and you start talking about data, the first thing that they show you is what they actually measure. So when a human has a cancer, and I have to tell you that if we don't cure that disease, if we are not already affected, we will be affected, all of us in this room. And they show you this kind of thing. They show you how they measure it. This is a CT scan of a woman who had medullary cancer. And then these people are always patients are always put on medication. When they're put on medication, this medication in 99% of the cases works, or at least for a while. And what they measure actually is the tumor quantity. So they take all these measurements here. I'm not going to, and I'll tell you in a second how they measure them. And you see that all these differential geometry models are, in this case, needed, but not used at all. And they see that the tumor quantity goes down, reaches some minimum, that's a typical thing, and then it starts to grow again. So you have killed some part of the cells, but other cells are not sensitive to your drug, and they continue growing. When they meet 20% above the minimum, it is said that the patient has a progressive disease, and it's taken off the medication. And then it's given another medication which does the same and then goes like this. If you're lucky, then of course you can go to 0 and never come back. We are very thankful now that for the last 5-6 years we can do this for melanoma. We have these immune wonderful drugs. In 20-25% of the people we have a complete removal of the disease. This is really great, but we need to understand why 75% don't do that. So how do we measure tumors? How do cancer oncologists measure tumors and radiologists? So I will show you here, it's a little bit of a scandalous actually situation, but it was started in 1976 by Charles Mortel, and he said, let me understand what does it mean to have a progressive disease. That is, what does it mean to be growing? So he took these spheres, gives them to oncologists, and say, can you estimate which is bigger and which is smaller? And they make huge number of mistakes, like 20% mistakes. And you can read the abstract, it's a really interesting thing. But he actually discovered that he quantified actually the error that people do. Now, of course, you can do now deep learning rather than shallow learning and use machines, but nobody's using it. This is the problem. So there are two criteria. There is the World Health Organization criteria for tumor quantity, and there is the RECIST, which is the United States criteria. And what they do is in the United States, using the RECIST criteria, they take the largest diameter, and this is a measure of the tumor. In the WHO, they take the two largest dimensions, multiply them, and take the square root. Now, this is the tumor quantity in the World Health Organization. And this is actually what is done. The only place where this is not actually done is in brain tumors, because we can use MRI, and because of MRI, there are a lot of physicists that have entered the field. And because there are physicists, they actually reconstruct the three-dimensional structure of the tumor. The problem with MRI in the brain, however, is very dramatic. I'm not going to show you the data, but the problem is that, so I'll give you an example. I was giving a data about 15 years ago when I was in Los Alamos from Mass General Hospital, from Rakesh Jain's study of a drug that was supposed to kill all the new blood vessels in the tumor. And so the data was fantastic. So these were like 15 kids, phase 1 trial. The tumor shrank. There was no evidence of the tumor after 3 weeks taking that drug. And then 3 months later, all the kids were dead. And this is because MRI measures water diffusion. And so the tumor was there. What they normalized was actually the water diffusion. So they actually removed the edema that exists in all brain tumors. The edema went away. The vasculature changed, and they didn't see any contrast. So it is very important to understand the physical mechanisms behind contrast generation, not only to analyze, because the images could be actually analyzed easily, but the image might be not of what you're trying to image. It could be actually the edema, or and you're not seeing the tumor. So be very careful when you're looking, if you're interested in looking in data from brain tumors, because you might not be seeing the tumor. You might be seeing other things. So anyway, so this is the criteria that is used. So what we try to do with NIH people is, why don't we go, take the WHO criteria, take the, so the WHO criteria I will call bivariate, that is you take 2 dimensions, take the RECIST criteria, the United States criteria, which is 1 dimension, and then reconstruct from CT scans the 3-dimensional structure of the tumors. And let's see whether we are making a huge mistake. Remember why this is extremely important. This is extremely important because patients are taken off drugs when the tumor quantity reaches 20% above the minimum. So now if the tumor quantity changes if you do the 3-dimensional structure versus the 1-dimensional measurement, you're taking these patients either before or after you need to take them off. So this is very, very important for these patients to know what is the actual tumor quantity and not maybe just 1 dimension of the tumor. And so we went to kidney cancer. We reconstructed the 3-dimensional structure using just tomography. And we measured the way the two criteria. So one is the World Health Organization, the other one is the RESIST criteria, and we measure the total volume. And surprisingly, however, when you plot them, you start to see that actually they're completely proportional to each other. And so we are not making a mistake. And the reason for that is because tumors have no structure. They grow, they don't respect the nice structure of normal tissue, which is a layered structure, which has cells really organized in layers and respecting each other. And these guys actually grow in a very, like a blob. And so if you take the largest dimension, this is the direction in which they actually have the least pressure from the other tissue to stop it growing. So you're really estimating the fastest growing population of cells. And we heard about the different populations here. And so you're not making a mistake. So really tumors are, as they sound, nasty things that actually blobs, they look terrible, and have no structure. And they're not actually part of life, they're part of death. But this is what happens. Now, how do they grow? This is another interesting story. Larry Norton, who is one of the leading breast cancer physicians at Memorial Sloan Kettering, wrote a paper in '76, and he said that it's a Gompertzian tumor growth. So this is exponential of an exponential, and he made a lot of noise and published a number of papers. If you look actually at the papers, at the data was very, very poor to show that there is an exponential of an exponential. And the idea was that the tumor is going first to grow exponentially, then it's going to slow down, and then it will level off. Unfortunately, when you have real human patients, this leveling off is almost never seen. The patients are dead way before the leveling off. And so we looked at data, and we tested a lot of models. So you can think of very simple first order kinetics. N to the power alpha is the power at which, so this alpha characterizes the manifold on which the cancer cells are growing. They could be growing in the bulk, and then just alpha is 1. They can be growing on a surface, then alpha will be the dimension of the surface, which is 2. And then you can have a fractal manifold. People have tried to reconstruct fractals, for example, in melanoma, in skin cancer. And then it will be some fractional power. But whatever power it is, you can solve this equation, and you can get the various forms of the number of cells growth. And so you can test this power and the exponential and linear. You can test it against data. So we tested actually all these models, different powers. And what we found, and actually, maybe I should show you first this. Okay, so first we tested the models on individual patients. Now the reason why you can compare individual patients you can average them because these curves are not averageable. But what I realized that if you take the curve from here, then if it is a sum of something that you're killing, and we actually showed that very nice paper that when you kill with different drugs, including immune drugs, general chemo, or molecular retargeting drugs, they all kill the cancer exponentially. And the same is true for antibiotics killing bacterial populations. And now, to go back to the origin, to something I said before, if you're killing something exponentially, that means that there is only one time-limiting step to death. So that means that all these drugs that eventually the cell dies through one thing. And we know what it is actually, it's a mitochondria. So this goes exponentially down, we know that. So if you take from here, the data is just exponential. If it's exponential, you can now normalize the initial point for all patients to 1, and then you can actually average them. Because you can take the log, you can match a G, divide by the G, and you can average them. And when you average them, we average 800 patients here. This is a prostate PSA growth. So this is the PSA, which is the prostate marker that is used after age 45 now, 55 in the United States, to look for prostate cancer. The PSA actually is a volumetric change, is a volumetric measure, because all cells release the PSA, so it's really measuring the whole volume. And if you average them, you see that the log is actually a straight line. So it seems that this is an exponential growth. And we tested another vaccine trial, and that also looked exponential. And then we looked at mice who are not treated, so there is no treatment here, there is no decrease in the tumor, also looks kind of exponential. And so we concluded that it seems that the tumor kinetics is very simple first-order kinetics. So you have an exponential killing, and then another population of cells that is growing exponentially. More trivial than, you know, it's like a high school, even maybe middle school in the UK mathematics. But this is what it is. So it's again, the cancer doesn't have much of a structure. It's not complicated like normal tissue. It just grows, it seems to grow exponentially. There is a huge fight in the community of mathematicians, physicists, engineers, how it is growing. There are papers being published left and right. Some people claim that it is power law. Some people claim that it is fractal. Some people claim that it is linear. But when you talk to oncologists, they all say, oh, we know it's exponential because we look at the data every day. So that's what it seems. So it seems that they're actually, there are two populations, one sensitive to the drugs, another population that grows. It seems that the growing populations are growing with the same growth rate. There is a paper we published recently for colon cancer. The reason why they grow with the same rate, it seems, is because in the late stage just of cancer, all the populations that were growing slower, they're already gone. And the ones that are left are actually kind of similar to each other, and they just go together. And we looked at the genes. So there is very little overlap between genes for growth and genes for drug resistance. And so we concluded that actually there is an exponential growth, and the only way you can have exponential growth is if all the cells or majority of cells are dividing symmetrically. And so we are kind of trying to kill the cancer stem cell hypothesis, saying that there are no cancer stem cells, that all the cells are cancerous cells, they just divide symmetrically. And you can understand very simply, if some of the cells stop dividing, that is, they divide finite number of times, you would get for a little bit an exponential, but then another exponential, but the envelope of that will be a straight line. So you can achieve exponential growth with not symmetrically dividing cells. They have to be dividing symmetrically. So you have to have 2, 4, 8, 16, and so forth. You can't stop at 16 and get another cell to divide now, because you get 16, 18, 20, 28, and so forth. Simple algebra, not even algebra. But anyway, so we are trying to kill that hypothesis. At least in late stage cancer, it seems that all the cells are dividing. So this is my acknowledgements, and I think I finished on time. Thank you. Yes.
So about your last statement.
Yes.
I mean, I could last 30 seconds passing for an oncologist, so not 30 minutes. But what people told me is that when the growth is exponential, it's, I mean, as you said, in the late cancer stage, but the stem cell hypothesis is also applying to the early stages in which you have, I mean, you're on the road to cancer and you start having, and so you believe at this stage also it's not...
No, in the early stages I actually believe that there are cancer stem cells. And actually we are looking at, I didn't want to show the data because we are not fully analyzed, but it seems that early stages actually is linear growth. It seems that it's actually exactly right, that they're dividing asymmetrically, really like stem cells, and it's growing linearly. But in the late stage, I think these cells are gone, or if they're not gone, they're very, very few, and the majority now. In fact, there is a very nice paper by Ben Simons 2 years ago in Ben from Cavendish in Nature, and they actually showed exactly that. At the early stages, it goes linearly, and then at the end, 95% of the cells are dividing, and it's growing exponentially. I mean, there is one way. I had this argument with a biologist. He said, no, we can get an exponential growth from division that are asymmetric. And so I start thinking how the only way to do it is if the division time is decreasing exponentially. Right? But there is no such phenomenon in biology. But if it is decreasing exponentially, really, you would see an exponential growth. Yes.
Well, can you comment a little bit that some of the radiation oncologists that I worked with? They have noticed a phenomena in which local control of tumor affects faraway metastatic cancer.
Yes.
So how does that fit into the model?
Well, this is complicated because it is true. Not only that, but also metastases are affecting the original tumor.
Yes. Yeah.
There is this receding hypothesis saying that tumors are receded from metastatic sites back into the main tumor, and that the surface increases faster than the bulk of the tumor. Well, it's not in this model, certainly. I mean, one has to make it more. But it's true that the primary tumor releases things that actually affect the far sides.
So, yeah, and
absolutely.
Controlling primary tumor really affects how you
Yes, no, it's more complicated. The problem is there is very little real quantitative data to work with. I mean, we can model it, of course. We can make very complicated models. We can make extremely complicated models. But the problem is that if there is no data, then it's like the impact will be small.
But in your model, you're looking at late stage.
Very late, yeah. These are patients that have metastasis. They have shown already they're in a clinical trial. These are from clinical trials.
So there, in your data, you should see the effect.
Yes.
Local
Yeah, but you know the data is very noisy.
So
The noise is very big. You can measure you measure patients every 6 weeks.
Yeah.
You can measure them. I mean, so the only place that people do that, and Francisca does that, but that's why she works with blood cancers, because you can draw blood, and leukemia and these kinds, you can actually measure every week. But in these solid tumors, you can measure in brain tumors, they measure 4 points. That's it. Because you can bring the patients every,
You will talk after because there's lung
And you
cancer.
can bring it not only because the patient wouldn't do it, but because FDA wouldn't allow you.
Okay.
Yeah.
On the issue of measurement, if I correctly understood you, it doesn't matter whether you take the
That's how it's.
geometric average of
The
something.
data is so noisy, it doesn't matter.
Yeah. On the other hand, you said with the example of these poor kids that the issue is with the
That's in brain tumors. Only in brain tumors. This is CT scans that I showed you, or PET. In brain tumors, MRI is the standard, but MRI measures diffusion, especially in this normalizing the vasculature, and or contrast that, and so, yes?
So, okay, please.
Cell division follows a circadian rhythm, I have learned recently.
All right.
Is this also true for late stage?
Yes, so there is a little bit decrease, it's like 28 hours rather than 24 hours. In fact, there is a paper recently that there is a paper recently that claims that cancer breaks the circadian rhythm of all organs in the body. And they claim that one of the reasons why people lose weight in cancer is because the circadian rhythm is destroyed. So if this is true, it would explain why it's not 24 hours but 28 hours. It's just they don't respect the circadian rhythm somehow. Everything goes wrong in cancer. So I was going to show you some data that I'm trying to convince to Laurent and Michael to do. I mean, they're convinced. We're trying to get the data now, but to look at cells shapes. So the cells, there is a paper by Don Coffey, who unfortunately passed away last week. He's a famous cancer researcher at Hopkins. He published a paper in '91 where they look at cells and they did Fourier analysis of the surface. And they showed that normal cells actually are pretty smooth, pretty much like circle or ellipse. But the cancer cells had a lot of fluctuations on the surface boundary. And as you know, there is a nice paper by David Mermin where they looked at classification of closed curves in the plane. And we can use LDTMM. I call it now LD square M square, which is simpler for me. And there is LD cube now, I learned, M square. But to use this actually to look at cell shapes and see, can we relate? So one of the big questions in biology, if you read the 10 big questions, one of them is to understand how the genome is connected to the phenome. That is how the genome defines the properties of cells. One of the properties of cells is their shape. So can we actually, and there is a person, TJ Ha, at Hopkins, who now can measure actually proteins in cells. He can label up to 100 proteins, and he can measure them where they are. So can we relate these proteins with the shape of cells as they become cancerous or old and normal? Can we relate the genome to the shape of the cell? And I think it would be fantastic to use the LD square M square, because it really gives you a beautiful way. Right now, all the physicists that work on this, so a lot of physicists work on this problem, so-called jamming transition. What they have shown is that actually if cells become more rough, their boundary, they kind of jam. They can't move with respect to each other. And when they're around, they are not jammed and they can move. But the only parameter they use is actually the surface to volume ratio. So this is like, I think in terms of some kind of an expansion, that this will be the first term of the expansion. And the LD square M square captures the whole expansion. So you can actually really quantify the cell shape and try to relate to the genome. So there is so much things that can be done.
Cells are so small. I mean, one cubic millimeter.
Small is very
billion
relative.
cells.
Cell is very small is very relative. A quark is how many orders of magnitude? Yeah. Yes.
Okay. Before you, there was a question.
Yeah, so I'll comment first. So regarding the shape of cells, it's not only about the cell; it's also where the cell is. Because you can grow a cell in different materials, like glass or a high rate.
Absolutely.
And they will.
But the question would be, given the material in which you're growing it, how different cells, cancerous cells, old cells, these cells, change their shape as they progress in but the same environment? Yeah, I agree.
My question is, so you said before that the tumor somehow grows in a very regular shape, and you think that is the lack of mechanical forces somehow dictating how does that tumor grow?
Absolutely. And the tumor, for example, in pancreatic cancer, we know that the pressure is higher. One of the reasons people believe that we can cure pancreatic cancer is because we can get the drugs inside, because there is a pressure. People are now trying to normalize the pressure in the pancreatic cancer. And we are seeing that actually there is more influx of drugs. But they're also removing the immune system. This pressure is depleting the system from the immune cells. I think Darrow had, and then, yeah, sure.
Well, it's just a timely remark about the cancer cells changing shape. You know, this feeds into the question of how do the white cells of the body recognize the cancerous cells?
Absolutely. Yes, so this is actually a huge problem right now. A number of physicists and mathematicians are working on the immune response and how the immune receptors recognize the cancer cells. This is extremely important, absolutely. But there is very little work actually on, I haven't even seen anything on shape and immune cell recognition. Mostly people focus on the proteins that are expressed on the cell wall and doing the immune. I mean, Kurt Callan's working on that, Arup Chakrabarti at MIT, but nobody's working actually on the shape, absolutely, I agree. In fact, let me just say one something about Darryl. He said yesterday about growth, that you're interested in growth. So growth is, I mean, you know the KPZ equation, the Kardar-Parisi-Zhang equation. So it's an extremely rich mathematics behind it, and there was a Fields Medal given in 2014 for actually making a breakthrough in the KPZ equation. But these all relate to stochastic because these are noisy equations. So one of the things that we need to figure how to use when we do cells in LD square, M square is how to handle the noise. Because the data is necessarily noisy. So I don't know, I mean, maybe you guys know how to put the noise in the scheme. It would be very useful to learn that for me.
Several people are going to be talking about
Okay, so thank you so. Yeah, that will be extremely important. Okay, well,
Yeah, this is the
see how much little I know.
exactly the new way.
Yeah. Okay, well, thank you.
So the fact that the cancer has this exponential growth indicates the breaking down of the feedback control. Otherwise,
Yes, absolutely, exactly.
so how many feedback circuitry do they have, and what how much do people understand such the
So,
mechanism?
not much is understood. What we know is from the wing development, work by Boris Schreiman and others,
Oh, okay.
where they actually can suppress some of these feedback loops, and then now the forces are not working. That is, the feedback loop is not working, and now this is growing. The same proteins are preserved also in humans, and so and they actually are mutated. Many of these proteins are mutated in cancer. So these feedback loops actually are broken, at least in these late stages. In the early stages, we have very few mutations. And there are some cancers. I have a friend, she has a lung cancer. She has almost no mutations. When there are almost no mutations, it's a terrible disease to cure because you can't find a target. So it's growing. It has 1 or 2 mutations. These mutations are not expressed on the cell wall. So you have nothing to target. All it's happening, these cells are just dividing. And yeah, it's terrible. But yes, the feedback control on the cadherins, so-called proteins, are actually mutated in many of the cancers. Everything goes wrong in cancer. So anything you can think of goes wrong.
That's the story.
That's the thing.
Okay, so
Thank you.
up here, thank you.